So let's look now at inverse functions. And this lesson, we're going to determine the inverse of a given function, determine whether two functions are inverses, and then graph the inverse of a function. But before we do, when we talk about an inverse, two functions are inverses if one function undoes what the other function, quote, does. Now, we looked at that with operations already. If we perform the operation of addition, to undo addition, we do the inverse operation of subtraction. Or if we were to multiply something, we could undo that operation by division. And there's many of them, such as square rooting something and squaring it. Again, one undoes the other, inverse of each other. The inverse function, though, is really just a reflection across the line y equals x. And in order for a function and its inverse to qualify as functions, the original must be a one-to-one function. So we're going to bring in that one-to-one function test and use it in more detail. But let's first determine the inverse. And determine the inverse is really just a four-step process. And we're going to do this in our example that we do. First of all, we want to first determine, is the original function one-to-one? If it's not, the inverse is then not a function. The inverse will exist, but it's not a function. Once we have determined that, then we can replace f of x with y and change all the x's and y's, solve for y, and then replace the new y with this notation f to the negative 1 of x. And this is only true if it's actually a function. Now, if that seems confusing at first, we're going to apply it when we do our example here. Here is our function, and we're going to determine the inverse of the function, the f to the negative 1 of this function. So if we go through the step-by-step process, first we want to determine, is this f of x a one-to-one function? And there's a couple ways we can do that. What we could probably do, likely the easiest, is think of the sketch of this function. It is a linear function down at -2, has a slope of 3, and we get a graph that looks like that. Once we get the graph, we can also then do our horizontal line test. And yes, indeed, a linear function is one-to-one, which means our inverse is also a function. We'll keep that in mind as we get to the end, but there's the first thing, verify that it's one-to-one. Well, now let's follow the next step. We're going to replace the f of x with a y. Everything else stays the same. And now we're going to exchange all the x's and y's. Reverse them. When you think inverse, think reverse. So instead of this being y equals 3x minus 2, it's going to be x equals 3y minus 2. There's our second step. Replace f of x and exchange x's and y's. Now it's just some simple algebra to solve for y. We can bring the 2 to the other side and get x plus 2 equals 3y. Divide both sides by 3, and we'll get a solution of y equals x plus 2 all over 3. There's step 3, solve for y. Now, step 4 occurs if the one-to-one function test was true. Replace this new y, and this is now considered our new y. We're going to replace it with this new notation, and we can use this notation of f to the negative 1 of x. That means the inverse of f of x, because our original function was one-to-one. Our original function is one-to-one, so our actual inverse is a function. And then we just write out what we have, x plus 2 over 3. There's the inverse of f of x, f to the negative 1 of x. And this one-to-one, whether to use the notation or not, we're going to spend more time looking at that. The important piece is to understand how to find that inverse and do some of that algebra. Well, why do we care? Well, it comes back to our composite function. If we have two inverses, they undo each other, and I use that term loosely. They undo each other. What that really means is if we do the composite f of g of x and do all the algebra, we're going to get x. If we do the same composite, but the other way around, g of f of x, we're going to get x. So in that rare instance, and this is where we use if and only if f of g of x is equal to x and g of f of x is equal to x, then we know two functions are inverses. Let's try an example. Let's see if these two functions, f of x and g of x, are inverses of each other. Well, we start with our composite function. Doesn't matter which one we start with, so let's start with f of g of x. That tells us we're going to put the function g inside the function f, which means everywhere there's an x in f, it's going to get replaced with 3x over 2x minus 1. There's our original x. And now we're going to replace that x again with 3x over 2x minus 1 minus 3. So doing the composite piece is usually pretty straightforward. It's the algebra that gets a little bit complex. So let's look at this algebra. We're going to keep the numerator the same, 3x over 2x minus 1, and all of that will be over 6x over 2x minus 1 minus 3. Now at this point there's a couple things that we could do. What I'm going to do here is multiply numerator and denominator by 2x minus 1. And what this is going to do is it's going to eliminate the fractions. We'll see here, we'll get 3x. I'll write it out the first time here, 2x minus 1. All over that 2x minus 1, we get happy because those are going to cancel. That'll all be over if we multiply both things by 2x minus 1. The first term will eliminate that fraction, and we get minus 2x minus 1. Again, as long as we do the same to both numerator and denominator, a bunch of stuff is going to disappear. And what we'll be left with then in the numerator is just 3x. And in the denominator, 6x minus, if we distribute this in, we'll get negative 6x plus 3, which becomes 3x all over 3, which becomes x. So there's our first piece for our composite function. When we did f of g of x, our final solution ended up being just x. Now, what I want you to try and do is do the composite function g of f of x and see what you get. When you do g of f of x, there's the composite, putting f into g, and from this point, it's just a bunch of algebra. Again, pause, see if you can get the algebra and get a final solution. And if we expand that all through and eliminate the fractions like we did in the previous situation, all of those denominators will cancel if we multiply by 2x minus 3. This will allow us to have 3x in the numerator and then 2x minus 3, which of course becomes 3x over 3, which becomes x. And only now, because both f of g of x was equal to x and g of f of x was equal to x, we could say f of x and g of x are inverses. And now we know they are inverse functions of one another. What if we don't have an equation? What if we have a graph? And if we're graphing the inverse, The graph of the inverse is actually quite simple to take because we're going to use our symmetry, and we've used symmetry before. They are symmetric about the line y equals x. If it's symmetric, it's just a reflection across that line, y equals x. And really, if we are graphing a function, when we reflect across the line y equals x, all we're doing is taking our original x, y coordinates, and when we perform the inverse of them, the numbers are really just going to switch. X becomes y, y becomes x. They just reverse around. Let's put that into practice in this example. Here's our quadratic function. X plus 2 squared plus 4 already graphed, and we want to determine the inverse of this function. Now, we don't care about the equation, we just want the graph. Well, the first thing to remember is that it's a reflection across the line y equals x. So let's put in that line of reflection. And we can enter that in as a dotted line like so. This is the line y equals x, where every x and y is the same. We are at 1, 1, 2, 2, 3, 3, etc. So how do we graph this reflection or this inverse function? Well, if we start at our first point right here, that first coordinate is at the point -2, +4. If we were to reflect that or do the inverse of that, we just reverse. We now go to the point 4, -2. There would be the inverse of that coordinate. So we would go to 4 and -2 and put ourselves a dot. Same could be said for that coordinate. It's at -1, 5, which means the inverse is going to be at 5 and -1, and we'll put a point like so. If we want this coordinate, it's at -3 and 5, so now we're going to go to 5 and -3, and if we follow that pattern, we will see our new graph with coordinates like so. And now that we have the coordinates, we just sketch the shape as it was before, the original shape, and there it is. It's like we've taken that parabola, turned it sideways, and we've reflected it across the line y equals x. And that's how we graph the inverse of a function given the graph. And we're going to continue to explore this more in class.